In 1964, Russian astronomer Nikolai Kardashev introduced us to the Kardashev scale, a method of measuring a civilization's level of technological capability. At Type 1, a civilization was defined as able to harness the equivalent of 100% of the energy that reaches its planet's surface from its local star. For Earth, that's about 200,000 terawatts of power. At Type 2, a civilization could harness all of the energy produced by its local star, usually by building a Dyson sphere around it. For our Sun, that's about 400 billion petawatts, about 2 billion times more energy than reaches our planet. At Type 3, a civilization could harness all of the energy of every star and every black hole in its local galaxy, about 100 billion times more energy than produced by our Sun. It may not surprise you that humanity doesn't perform that well when measured on this scale yet. We command about 0.16% of the energy that reaches the surface of our planet, which is kind of embarrassing. But a recent breakthrough just announced this month might change that. This is the first successful creation of a new class of technology. It looks like a normal silicon cell, but it isn't. It is a step change in how we collect the power of the sun. It makes use of a material, Perovskite, whose promise has been talked about for a very long time, much like the inevitable dawn of fusion technology. But unlike fusion, this actually now works. And as of last month, you can actually buy one, at least if you're an energy company. To find out more about this technology and why it may be unlocking the next generation of cheap, clean energy, I went to visit a team of scientists in Oxford, in my most flattering outfit yet, to meet Dr. Chris Case and his team, who are the current pioneers and leaders in the field.
We're making more efficient solar cells than silicon, and more efficient solar cells than silicon could ever be turned into.
But how does this technology actually work, and why did Oxford PV win in a sea of other teams trying to advance this technology? To understand that, and why the future is not silicon, we first need to understand how we got here. But first, I have to thank today's sponsor who makes these deeper dive videos possible, Opera. When I'm researching new breakthroughs, I've got a pretty specific routine. I need all of my ideas and research tools easy to access, and that's why recently I've switched over to Opera's desktop browser. My favorite feature is the sidebar, which allows me to access everything quickly and is especially useful for keeping on track of my social media accounts, or to listen to music while I work. I also really like that when searching the web, Opera has a free ad blocker and VPN built in with no third-party extensions required. Opera also has brought in Aria, an AI feature that I use to speed up my workflow. When I'm reading an academic paper, I'll come across a term that I need more background information on, and if I want to know more about it, I highlight the term and hit explore, and Aria will automatically explain it to me. If you then have further questions, you can hit Control and // and Aria will pop up to answer your questions. Aria can also create an image that you want from scratch, interpret images that you upload, and even translate text to speech if you prefer listening rather than reading. If you guys are interested in a more fluid internet experience, check out today's sponsor, Opera. You can use the link in the description down below or the pinned comment for more info. Now, back to the video. In 1839, French physicist Edmond Becquerel observed that when he placed two electrodes in a conductive solution and exposed that solution to light, it produced a small electric voltage, too weak to actually do anything useful with, but marking the discovery of a phenomenon called the photovoltaic effect, turning light into electricity. This breakthrough intrigued the scientific community, but it wasn't until 1883 that Charles Fritz found that by taking a sample of selenium, a material also found to present the photovoltaic effect, and applying an extremely thin layer of gold to it, he could increase its efficiency to a mind-blowing 1%. This was the world's first solar cell ever produced, even if it was kind of bad. In 1887 though, Heinrich Hertz, a physicist famous for only doing one task each second, was trying to generate sparks between two metal electrodes. Through as much accident as science, he found that the sparks were easier to produce when his equipment was in the presence of ultraviolet light, as if the light was capable of knocking electrons off of his material. What he found particularly surprising was that for his specific material, only light of UV frequency or higher had any effect. If he used a lower frequency like normal visible light, even if he turned up the brightness all the way, the effect was never observed. This is interesting because in building solar cells, we also see this behavior. Below a certain minimum wavelength, they can't generate electricity. But why not? For that answer, just like most stories in physics, we needed to wait for Einstein's help. He suggested that light isn't a continuous wave, but a collection of quantized particles called photons, with each photon having a characteristic energy level that depends on its frequency. As it requires a certain amount of energy to break the attachment of an electron to its local atom, only photons of a certain frequency or above have enough energy to break the electron free. This phenomenon was later termed the photoelectric effect, and in thanks to Einstein for this breakthrough in understanding, we gave this otherwise quite obscure scientist the only Nobel Prize he ever received. When we talk about this phenomenon in solar cells, though, we think of this as an energy band gap, a minimum energy required to free an electron from the outer valence band of an atom to the conduction band, where electrons can move freely and create electrical currents. The lower that band gap energy, that means the larger the selection of frequencies of light are capable of freeing an electron. Now, this sounds like a good thing for collecting as much light as possible, but there is a catch. Photovoltaic cells are made by combining layers of electron-rich material, N-type material, with electron-poor materials, P-type materials. When combined, the electrons at the edge of the electron-rich material rush over and combine with the holes of the electron-poor material, and create a neutral depletion region between the two that has a strong electric field across it. When a photon from the sun hits the depleted region, if it has enough energy, it is capable of freeing an electron, creating an electron-hole pair which the electric field pushes to opposite sides of the device. As the electron makes its way through the material, any energy above that required to first free it from the atom is slowly lost to heat. As a result, the voltage between the two sides of these materials when we later connect them with a wire to extract electrical energy is only ever proportional to the energy required to break the electron free of its atom in the first place. So small bandgap materials collect a wide range of frequencies but produce only very weak voltages. Large bandgap materials, by comparison, can only collect a narrow range of high frequencies, but they produce higher voltages. Both approaches waste energy and create inefficiency, which is something we worry about if we want to ever make our way up to that Type 1 civilization. To quantify this trade-off, in 1962, Shockley and Quasar characterized the balance of bandgap energy against how much of the sun's spectrum a material could collect, and came up with this efficiency distribution, suggesting that materials with a bandgap comparable to silicon were the best choice of solar cells. Conveniently, 8 years earlier, on April 25th of 1954, Bell Labs had already started work on silicon solar cells, and produced a good for the time but still kind of embarrassing cell with an efficiency of 6%. On this news, the New York Times proclaimed that silicon solar cells would lead to the capturing of the limitless energy of the sun, but unfortunately, they were kind of wrong. According to Shockley and Quasar's work, the maximum theoretical efficiency of silicon could never exceed 30%, and actually, despite a further 70 years of innovation after Bell Labs' breakthrough, the best commercially available silicon solar panels are actually more like 18 to 20% efficient, and are pretty much stuck at that limit. The interesting question here is, when the laws of physics say no, how do you use engineering to do it anyway?
In the face of overwhelming odds, I'm left with only one option. I'm gonna have to science the shit out of this.
Many teams around the world came up with a similar answer to the problem of silicon. What if, rather than constructing a solar cell out of just silicon, instead you construct it out of many layers of different materials, with each additional layer tuned to absorb a slightly higher energy part of the light spectrum, so each layer maximizes the efficiency of the energy captured from each photon.
And in fact, if you take the concept to the extreme, your most efficient version of a solar cell would be an infinite number of semiconductor materials, each one designed to absorb only the narrowest portion of the spectrum and deliver the electronic energy.
This is a great idea in theory, limited by one simple, more practical problem: cost. In practice, producing just a couple of layers called a tandem cell actually already makes a dramatic improvement.
The step change from a single junction to a two junction or tandem solar cell takes your theoretical efficiency from somewhere between 27 and 29, depending on the exact material, way up into the 43. So a step change in the potential conversion efficiency for your solar cell.
So now humanity had a design, it just needed a material to help make this happen. And we found it in perovskites. Perovskites were first discovered in 1839, the exact same year that Becquerel discovered the photovoltaic effect, a coincidence that I always find kind of suspicious. Perovskite refers to a specific crystal structure rather than a particular elemental composition. All perovskites have a positive center and corners with negative atoms on each face. As a result, a large number of different elements can be combined together in this form, allowing researchers to engineer crystals with a wide variety of physical, optical, or electrical characteristics.
Largest uses of perovskite materials in the world, developed mostly in the 70s, are the high-temperature superconductors used to cool magnetic resonance imaging systems. They are the standard material. So perovskites have been used for decades commercially.
They can also in particular be engineered to absorb specific bands of photons very efficiently, so efficiently that for the same absorption capability as silicon, perovskites only need to be 1/200th of the thickness, or about 100 times thinner than a human hair. This means both less material is required, so a lower cost to produce the unit, and that they can be layered without making a bulky device, even to the point where they can be made into these flexible devices like you see here. Though this one that Oxford PV has developed is at an early stage, and very sensibly, I wasn't allowed to touch it. What I found interesting was that when you make traditional silicon cells, it is incredibly energy intensive and complicated as a process. Silicon cells have to be monocrystalline, meaning that a single near-perfect crystal structure exists, otherwise it significantly reduces the cell's efficiency. You grow a silicon cell from a single seed crystal, and they come out as a giant silvery mass that is then sliced into perfectly flat layers, not a single atom out of place. By comparison, perovskite manufacture is significantly easier. Oxford PV weren't allowed to give specific details as to how they manufacture their devices, but common approaches in the industry are screen printing, spin coating, or sputtering, all infinitely easier and cheaper than silicon. Each sample is then measured under as close to sunlight relevant conditions as possible on equipment like these solar simulators.
This particular setup is a solar simulator designed to reproduce not only the solar spectrum, but the solar intensity of the sun in a contained environment.
Then the team took some time to show me what these materials actually look like under an electron microscope. Totally disorganized and chaotic looking compared to the pristine surface of a silicon wafer, like a sea of tiny boulders. Obviously these materials still require significant tuning to get the best efficiency possible, but the bar on difficulty and cost for producing just a functioning perovskite cell is significantly lower than silicon.
And so the perovskite, it turns out, has very good properties to enable that to happen. So we call it defect tolerant. So if you have inevitable impurities, so material impurities, or crystal imperfections, either within the crystal structure itself, or within the film or the block of material that we're using to do the absorption, you need those defects to not result in efficiency losses going in that chain of events.
However, despite being defect tolerant, perovskites aren't without their problems. What's kept them from the market up until this point has been just how easily these thin films degrade. If exposed to moisture, oxygen, a bad attitude, any negative environment rapidly reduces their efficiency and lifespan, making real-world use basically impossible. This is why they have quite so many high-five machines throughout the lab. All development is done in protective environments free from moisture and oxygen, making developing reliable devices a slow and systematic process. As a result, making a successful device is a significant challenge because the innovation space, the range of possible things that you could assemble and call a perovskite, is huge.
Something like 500,000 possible compositions for perovskite solar cells. You could try out 500,000, but you don't want to.
Oxford PV have tested thousands of different combinations of perovskite, and if you think about it, each additional layer of perovskite you add absorbs a slightly different color, so is made of a slightly different material, which may behave slightly differently depending on the layer above and below it. So suddenly you start to understand how large and complex actually building a working device becomes. Despite the challenge of this field, teams around the world rushed to embrace perovskites and have been working on them for a little over a decade. Many breakthroughs have been announced which are interesting for their technical ingenuity, but at the end of the day, you want to make something that actually works. And that's where Oxford PV were the first to say, how do we maximize the capability of a perovskite while minimizing the risk and timeline to get a breakthrough into the hands of the world? And that's the sort of engineering question I always find really compelling.
In order to get that new cell technology out into the market, out into the world and doing good as quickly as possible, you want to piggyback on the capability that's already out there. That gives you the early opportunity to take this perovskite and you apply it as a thin film coating the second cell simply on top of what is now a very highly developed, widely available and manufacturable silicon solar cell.
In 2014, Oxford PV were, as far as I can find, the first team in the world to switch to a silicon perovskite tandem cell design, focusing on designing just a single new perovskite material tuned to be effective at absorbing the bluer, higher energy photons, and then relying on a well understood, highly optimized silicon layer below to absorb the lower, redder photons. Through this approach, over the last few years, they have been able to produce a cell efficiency of about 28% already, basically at the theoretical upper maximum limit that silicon could ever reach by itself. Many other teams around the world were making similar sorts of breakthroughs, but the problem most were encountering was that they could produce these in the lab, but never successfully manufacture them at scale. In 2017, Oxford PV opened the world's first volume manufacturing line for perovskite on silicon tandem solar cells, saying a core part of their innovation strategy needed to be making these things scalable as well as efficient as possible. The unit efficiency, which they now quote, which is differentiated to the cell efficiency, is already at 24%. That is 20% higher than the best commercially available silicon solar cell on the market. This slight drop in efficiency from 28% is because additional layers of packaging are needed to take a lab material and turn it into a material that can survive in the real world. The question is, why does this all matter? It matters because it allows us to use now smaller footprints for new energy installations while still getting the same amount of power out of them, or to get more power out of the existing land we've committed to these projects. But of course, this advancement does not come without a cost.
It is not cheaper. It cannot be cheaper because we're taking an ordinary solar cell and we're adding another solar cell to it. So there's got to be the additional cost. So it is more costly to make. But the question you should ask is not how much does it cost to buy that panel or solar cell, but is the energy that it generates, is that cheaper than the energy from an ordinary solar panel? And the answer is absolutely yes.
Having said this though, over the last 10 years, silicon solar cells have dropped in price by 90% to be the cheapest alternative energy source. So building on top of this infrastructure isn't a bad way to start. Knowing that the efficiency can continue to scale just with tandem solar cells up to 43%, even before investigating increasing the number of layers. And hopefully by that point, the manufacturing process, the costs and the lifetimes of these materials are all much better understood. And the next generation of these devices can push even closer to perfect efficiency. I found it really interesting the work that Oxford PV are doing because so much of how they think about this problem comes down to just great practical engineering. In my job outside of YouTube, my whole role is to say not only what teams are working on problems that matter, but also who can actually deliver on the promise of their idea. I would say the former purist physicist in me, I think absolutely would have said, how do I innovate perovskites on top of perovskites to see the perfect outcome of what this technology could become? And I've heard many academic and scientifically trained folks vocalize the same idea of the perfect outcome is better than the outcome that works in the near term. Sometimes I think finding a practical solution that gets you there much faster is in fact much more important. Here I think Oxford PV had demonstrated a really good set of choices, balancing huge complexity risk with a series of practical engineering decisions that simplify their lives, minimizing the risk where they can and innovating where they have to. Many teams around the world are still innovating in this space, and there will absolutely be breakthroughs and already have been reports of higher in-lab efficiency. At the end of the day though, what matters is delivering on the promise of these ideas, and sometimes in these races you're betting just as much on the jockey as the horse in the race. In 1973, when Carl Sagan discovered Kardashev's work and adapted it after also feeling embarrassed we didn't make it even to a Type 1 civilization, he defined a Type 0 civilization as one that could control about 1 megawatt of power, the equivalent of 100 campfires burning continuously at any given time, the definition of the rise of civilization. He found that 1970s humanity was using about 10 terawatts of power, giving it a Kardashev rating on his scale of 0.7. Today, 50 years later, despite using twice the amount of available power, we're at about 0.73. But progress usually comes in jumps and starts. Maybe it is this new generation of technologies that can speed our progress along this curve.
470 exajoules of energy reach the Earth's surface every 8 minutes. That's the same amount of energy that the entire planet uses in a year. So there's a lot of energy from the sun. It's got at least 4.5 billion years left to run, so we're not worried about it going out of business. It's never raised its price, so the sun is the perfect energy source, and the sun's a good thing.
Thank you so much to Chris, Ed, and the rest of the Oxford PV team for being so eager to show me the technology and for giving me the Willy Wonka and the Chocolate Factory feeling, and I guess outfit, of being at the frontier of humanity's capability. If you liked this video, leave a like below and let me know what other technologies you would like me to take a look at. And thank you guys, as always, for watching. I will see you all next week. Goodbye.